What's up, my friends? We're going to integrate x squared times e to the negative x squared from negative infinity to infinity, and it's going to be awesome. It's going to be super short. The first thing we're going to do is use the fact that this is an even function, and because of that, we can rewrite the integral as 2 times the integral from 0 to infinity, because when x is negative, the function or this integrand will have the same value as if x is positive for any given x. Okay, and I also split up this x squared into x times x because we're going to use integration by parts. And this is the template formula we'll use, and we'll set u equal to x and du equals dx. Now we'll set v equal to x times e to the negative x squared dx. And you might be able to integrate this right away in your head, but I'm going to do a substitution. I'll let n equal to negative x squared. Now if we take the derivative, dn dx equals negative 2x, and we can substitute that in to give us this value for b after integrating. So if we integrate, the left-hand side becomes v, and if we integrate, this right-hand side becomes e to the n, because negative x squared is n. You see that? And this x times dx, if we rearrange this equation here, multiply both sides by dx and divide by negative 2, we get x dx equals dn divided by negative 2. Okay, I hope that's clear. Now we can integrate e to the n. That's our friend. It's itself. E to the n. And this negative 1/2 comes along for the ride. And now I'll just rewrite this in terms of x rather than n, because we're dealing with x. And n is negative x squared. So I substituted it back. Okay, so we can plug all of this into our integration by parts formula. And I have a couple things here. I have limits, because this u times v, because we're dealing with limits here, we need to include the limits for it. We'll go from 0 to b and make the limit as b goes to infinity. Great. And this x is our u, and this part in the blue is our v right here. Okay, minus the integral of v du. And these 2's here, see these 2's? These 2's are here because of this 2 right here. It comes along for the ride. And this part in blue, that's our v, and our du is the part in green right here. Okay, so if we evaluate this first part, we get this right here. This negative is right here, comes along, negatives here, and these two cancel out. Now we want to evaluate this as b goes to infinity and at x equal to 0. Well, in the limit as b goes to infinity, this is what we're evaluating. We're evaluating b because this x becomes b divided by e to the b squared, because e to the negative x squared becomes e to the negative b squared, and if it's negative, it goes in the denominator, right? And then we can just plug in 0 for x because there's no problems in this other term. Now, to evaluate this first one, you might be able to see that it goes to 0 right away, but we should pause at it quickly. So we can evaluate this kind of graphically looking at it, where the numerator b is modeled as like f of x. It would be like a straight line. And if we were to write the function e to the b squared as a function of x, we would say g of x equals e to the x squared. And we can see that the denominator is growing at a faster rate compared to the numerator. So because of that, we'll get a larger denominator. That's going to become infinitely larger than the numerator, and it's going to go to 0. We can quantify this using L'Hopital's rule, where the limit as x goes to infinity of two functions divided by each other, if they're indeterminate form, like infinity over infinity or 0 over 0, it's the same as the limit as x goes to infinity of the derivative of those functions. And the derivative of these, the numerator and the denominator functions, as the numerator becomes 1 using the power rule, and then using the chain rule, the denominator becomes 2 times b e to the b squared. And at this point, my friends, I hope it's obvious that this has to be 0. The numerator's stuck at 1, and the denominator becomes infinitely large, so this whole thing goes to 0. Okay, so this limit term goes to 0. This other term goes to 0 because we have 0 over 1 in the denominator. And this other integral is a bit of a beast. It's not too bad. I derived this, or I should say I evaluated this integral a number of different ways. It's root pi over 2. It takes a couple minutes or longer depending on your method. Some are faster than others. So you can check out my videos on those other methods. It turns out to be root pi over 2. And at this point, my friend, we've evaluated our integral. This whole first part becomes 0, and then we just have root pi over 2, which is our answer to the integral. I know integrals are not easy to learn, but the more you do, the better you'll get. You can survive. Hang in there. Cheers.